just in case. So we'll have backups. Okay. So want to do like a design, not full design session, but it's mostly driven by you guys. I'm going to be asking questions kind of. So you just suggest how you might implement this. So the goal is to implement the univariate polynomial in Rust. We need two functions. We need evaluate and we need interpolate. So evaluate is supposed to take a value for x, right? And then give you the corresponding y output. Then interpolate is supposed to take a set of points and then give you back a univariate polynomial. Does that make sense? So this means that we need a representation for the univariate polynomial, right? So there are three things we need. We need a representation for univariate, like a way to represent a univariate polynomial in code. We need that. And then we need to implement the two functions, evaluate and interpolate. So the first thing we would brainstorm on is the representation. Okay? So you don't have to do it a certain way. It can be any way, right? As long as it works. So you have like your test for it and you make sure that you can actually like evaluate. You can represent any univariate polynomial. So if I give you like 2x squared plus 3x, you should be able to convert that into your representation. And then when I say, okay, evaluate this polynomial at x equals 5, you should have a function that can do that and give you the corresponding answer. And if I say, okay, I evaluated this function at 3 points, I want to get back this 2x squared plus 5, you have an interpolation function that can go backward. So the starting point is basically representation. So
we're currently here.
So the starting point is representation. Let's focus on representation now. Who has ideas on how you might represent a univariate polynomial in code? So something like let's say we have 5 structs. Then you have 2x, let's say plus 5. And let's say you have 3x squared plus 2x plus 5, right? So these are 3 different polynomials, technically. You need one representation that can somehow encode all of this. So you know how to represent this in your representation, you know how to represent this in your representation, you know how to represent this in your representation. So how do we do this? Coefficient and the exponent.
Yes.
Okay. So
For each term.
So everything in between the plus, right?
In between what?
The plus sign.
Okay,
so like 2x and 5, right?
You store them as monomials at first.
As monomials.
Yes.
So you're going to have another struct called monomials.
No, maybe not necessarily.
So what would it? A tuple?
Okay, if you have a user would want to like impute the polynomial into there will be a function for that, right?
Well, you could just create a struct, yes.
Okay.
Mm-hmm.
Then maybe you can sum have like a vec that stores them.
Each term, right?
Yes.
Each monomial. Yes.
I don't think what she said, is it necessary to store the exponent?
It's important, I guess.
No, because I feel like it's kind of like predictable. Like if you look at it, it's kind of predictable.
For this one, but when you have like x raised power 7, what's the
So because even if you know you have
Yeah.
think you know how to write plus x raised to power 0 at one point. So it's kind of like predictable. We always know that when we have a polynomial, there's always like an x raised to power 0 part that goes up to even the x raised
It's
to
not
power 0.
every polynomial that is like incremental.
I'm enjoying this.
No, but you can actually make it increment. Even I know that it can be like x raised to power 7 and maybe plus x raised to power 5, skipping x to power 6. But then that is actually there, but coefficient is 0. That's what I'm saying. So we know that it is predictable because
Okay.
it follows that pattern.
From what I'm exposed to right now, like there's a way to actually like have like a number of monomials in the vector store, just passing the number of monomials, and that way you can actually put the first monomial, the second monomial exponent and the coefficient, second one and third one.
What is it? You mean okay, exponent and coefficient, okay.
Yes, I
But
store them.
So what you guys have discovered now is your own is sparse. That's the sparse representation, and yours is dense. So there are two ways to represent polynomials. So yours is the sparse representation, and yours is the dense representation. That's why I was enjoying the fight. So I'll show now how so I'll start with yours now. So in her case now, she's saying that you put each monomial in a vec, right? So you have for every item in the vec is a monomial. Then every monomial is made up of, since it's univariate, only one variable, right? So it's made up of a coefficient and an exponent, right? So in this case now, let's say the 5, it could just be like a vec of that has just, no, not really sure. The exponent is 0, right? So depends on the one you want to put first. You might want to put the coefficient first, then the exponent. So let's say you're putting the coefficient first. So 5 and 0, right? That represents that polynomial up there. Then there's another one, which is this. So in this case now, you can put 2, right? Coefficient. Exponent is what? 1. And the other one is 5. Exponent is what? 0. So this contains the same information as the other one. Then this other one here, you can do the same thing. You could do, so what would this be? It's sparse. It's sparse. So it's like, you're not wasting space, technically. I'll show you what the dense looks like now. The advantages and disadvantages to both sides. It depends on what you're trying to do. Okay? So this is the sparse representation. So you're like as literal as you can be to the actual equation. You're just putting it there. But then there are cases whereby you don't want to, it's predictable, like you were saying, right? Like, not that it's predictable, you make it predictable. So in this case now, you could technically have been like, okay, let's say this 3x squared plus 2x plus 5. Technically there's an x raised to the power of 0 here, right? So if you look at the power is growing sequentially, technically. So this is like power 0, power 1, and power 2, right? Which is the same with the index of an array, okay? So you can take the index of an array as the power. So this means that, you know that, okay, index 0 is going to be associated with x raised to the power of 0, which is the constant. Then index 1 is going to be associated with x raised to the power of 1, and index 2 is going to be associated with x raised to the power of 2, right? So this means that you can now put just the coefficients there. So you just put here, well, this will be what, 5, this will be 2, and this will be 3. Does this make sense? This is a dense representation. So you have an entry for every possible power of x. So this is now where things get, so you can see now in this case, this is a lot more succinct, right? Because it's just like straight. Exactly. So now imagine if you now had x raised to the power of 1000. You get the problem now. So if you had, let's say, like your polynomial was 2x squared plus 3x raised to the power of, let me not do 1000, let's do like 7. Yeah, right? Now in this case, in the sparse representation, this is just what? 2, 2, 3, 7. In the dense representation, you now need to blow it up. Yes. So you have a constant 0, then plus 0x, right? Then plus 2x squared, then plus 0x cubed, plus 0x4, plus 0x5, plus 0x6, plus 3x7, right? So then your representation will just be like an array that has 0, 0, 2, 0, 0, 0, 0, 3, right? Exactly.
For that then, we don't have to follow a particular order.
You can choose your order. But the important thing is you know your order,
Yeah.
right? So you could go this way, you could go that way. You choose your order. But what you need to know is you need to know what order you have chosen. Because you need to be able to interpret any array like this. Does this make sense? So, I think when we were implementing, I implemented dense, right? And you implemented sparse. So it doesn't matter. Anyone can work. There are obviously trade-offs, but right now I feel like you guys should just choose the one you want. You like sparse?
I think we should
Huh?
analyze the trade-off. I think we should analyze the trade-off.
You want to analyze the trade-off? Yeah?
Yeah, I think we should analyze trade-off so it will give us more insight as to why we should pick one.
Yeah. So the thing now is that we now need to start looking at the evaluation. How to do the evaluation, for example. Then we'll now try and see, okay, how can you do evaluation in both cases, right? So you see whether one is better for you get that. Okay. So but that's going to be on you guys now. I'm just put it on them, right? Yeah. You just want you can ask now.
Does everybody understand the two representations? Everybody understands the two representations. Okay, so based on the two representations, how can you get the degree of
Nice.
the topic with the highest power, that was at the degree. Right for yes, yeah, for the okay, so for the sparse, the tuple with the highest power, and for the dense, the length of the array.
So the days will be easier, will be faster.
How about the vertical?
I think it's saying that you should be more precise with your algorithm. Like,
Sparse to be the top part index 0. While for the second item in the top part index 0. While for the dense.
yeah, but now give
Said sparse is not follow order, so you could.
yeah, it could be any order.
So you can see the first one example.
Actually,
Man, I'm not
yeah,
between
so
the-
you have to do it.
All the experiment. So you need a what? You need a loop now, right? Huh? You said you could store what? You can make it more efficient. You can make it more efficient. But do you get that? So how do I put this? There's no right way per se, right? There's no one way. There's no like, okay, this is how you must do it with sparse. Because technically you could have a sparse that also has, like you know it's a struct, right? It has the coefficient exponent tuple, right? But you could also have another field called max. It's still the same thing, technically. I was thinking maybe you'll be seeing each tuple one at a time. Then you can just keep track in your head, like, oh, the highest I've seen so far. So that whenever someone asks you for the degree, you don't need to go and check everything again. I don't know again. At the time you are creating the sparse, you could note the highest degree you have seen, so that it's as fast as the other one. So that's why I'm saying there's no one size fits all. Just look at the algorithm that you have and measure how fast it is and see if you can come up with a better way to do the same thing. Yeah?
You can draw.
Okay, so you can actually, just like Oba said, that you can look through the array of tuples.
Yes.
Now, when you look through the array of tuples, you can actually get, so you can hold a variable, and for every loop, you store like the index, the index one, like store it there. Then check if what is there is greater than the next iteration. So if it's greater than the next iteration, you set that variable to the new one. So at the end of the iteration, the one that is holding in that variable, you return it. That will be the power.
The degree.
That
The highest degree. The highest power, sorry, which is the degree. Yes. So that's how you can compute it. So you can do that every single time that someone requires the degree, or you can, like, once someone requires the degree once, you cannot store it somewhere, so that subsequent requests. But that's now an optimization that is not necessary per se, because people don't call. It's only necessary when, let's say, someone is calling the degree a million times, and you're like, oh, I don't want to recompute this thing every single time. But if you're only calling the degree once, then why waste that space you get? So it all depends on the context that you're working in. But I'm sure there are other ways to figure out the length, and there are other ways to represent things. But the degree question makes sense, right? So now we know two representations. I'm sure there are other representations. If you come with another representation, let me know. Yeah?
Okay.
Sorry, please, can you go over the dense representation again? I
Okay.
was a bit distracted.
So for dense representation, you need every power of x. Okay, so if there's a missing power of x in your equation, you need to fill it in. And it needs to be in some order, right? So let's say you had 2x cubed plus 5, right? In this case now, I'm missing x squared and x, right? So we need to expand it. So this 2x cubed plus 0x squared plus 0x plus 5. So now it's expanded. So your dense representation is just like the coefficients. Not this way. It depends on how you want to do it, yeah, but it's usually better the other way, where the coefficient, the index is actually the power. You get, because it's much easier.
You said it's usually better the other way. Or is there like a fixed?
There's no fixed. There's no fix. It's an algorithm.
The lowest.
It doesn't matter. No. So you can do this one, right?
Yeah.
Which is easier technically.
Yeah.
But then that doesn't stop you from being able to do this. You just have to know what order you are working in, and know that, okay, like this is 2 times x raised to the power of 3, right? So technically that's the same thing as like the length minus the current index. This is the length minus 1 minus I. I don't know how to put it.
So
Like,
this is the
yeah, that's the representation. Length minus, that's dense representation. Length minus 1 minus I will give you the power in this case. And then in this case, I will give you the power, right? So just know what order you are working in and what the true representation is, and then you can find the mapping.
So you wrote
Length minus 1 minus
3002
I.
and then is it 3002?
5. Don't mind my handwriting. Yeah, you want to say something? Length minus 1.
Length minus 1 minus. I'm trying to understand how that works.
That's, I hope it's correct, Sha. But the length is what? Length is 4, right?
Yeah.
So if I wanted to get the power of this, that would be 4 minus 1 minus 0, which is 3. Yes. So this 2 raised to the power, 2 times x raised to the power of 3, right? And then this one is 4 minus 1 minus index 1, right? Which is 2. So that's how you can remap it to the power. So it doesn't matter. It all depends on your context and what you're trying to optimize for. Make sense? So we know representation, we know degree, computation. So now let's think about evaluation. How might you evaluate the sparse polynomial? So let's say you're given that x is equal to some value, and you know the sparse representation, which is this. How might you compute the value or the result? Someone that's not answered before, please. Okay, so you have a polynomial, right? Let's say this 2x squared plus 3x raised to the power 7. You can evaluate at any value of x. But now we have figured out a way to represent it in code, right? Which is like using this array of tuples The question now is like, given this representation, how can we implement the evaluate function? That takes the value of x and gives you the results. I say this one is 2. Let me see whether we had a simpler. So let's say this 2x plus 5, right? This one here. If I evaluate this at 2, that will be 4 plus 5, right? Which is going to be 9. So given just this and 2, what algorithm am I going to use to get 9 out? Does anyone have an idea?
So given what?
Given the array.
Given the sparse representation and the value of x, compute the evaluation of the polynomial. Do you get?
Yeah.
Yeah.
You are giving us. So I think 2.
Wait. You wanted to say something, right?
Yeah.
Yeah. Go ahead.
I was thinking if you put it like in a variable and then just do like the whole arithmetic weight. So we'll be accessing values from the tuple. So
Okay.
like we have a variable for x, which is our only variable since it's univariate.
Yes. Which will be a concrete value now, right?
Yes.
Okay.
So it will hold that
Concrete x value.
X, yeah. Whatever. Let's say we pass
The
it.
x, yes,
Yeah. So we now have a variable that says 2 multiplied by. That means that the first 2 we are accessing it from.
The first tuple, right?
Yeah.
That's the
Accessing it
coefficient.
from here,
Uh-huh.
and multiplied by what we have in our variable that we set for x.
Mm-hmm. Oh, the power.
The power will now access it from the tuple again.
Okay.
So if it's 1, it will be exponent 1.
What will be exponent 1?
The variable.
The x, right?
X, yes.
So you have to do that first, right? Before you multiply with 2,
Yes.
right?
Yeah.
Okay.
So we use like parentheses for like the word mass.
Okay. And the other first, yeah, okay, yes.
So basically, what I'm saying is we just create the expression and store it in the variable so that when it evaluates, we get the value stored in the variable and return it.
We create which value? What expression, sorry?
Kind of like 2x plus 5 now.
Yes. You don't
What
know
I'm
that.
saying is-
You knew this, right?
Yeah.
Then you converted it to this representation. So this is what is in the computer's memory now, right? You are forgetting about that one, right? So now giving this and giving 2, what is an algorithm that you can use to compute, not necessarily 2, giving this and giving any value of x. What is an algorithm that you can use to do the evaluation? So what you were saying now is you need to go through each tuple, right? And compute something from each tuple. So first tuple, what are you doing?
We are going to.
The x value, right?
Yes.
Times what?
Well, 2 is the coefficient, right?
Yeah, the coefficient is 2.
It's 2.
Sorry, let me change this thing. Let me change it to x. So let's say this is 7 now. Okay, continue.
Sorry, I'm confused. What's the 7?
The 7 is the x value.
The value you're trying to
Okay,
evaluate.
yeah. So now we say 2 times 7 raised to the power of 1.
Yes. Okay.
Then we say plus
X.
5 times 7 raised to the power of 0.
Yeah. Yes. So you compute, then you sum. And you compute for all the terms, then you sum everything. Yeah. So in ROT, you can use like a map or a reduce or folio and so there are multiple ways you can do it. But that's technically how you would evaluate like a sparse. Does anybody have another way to do it? Okay.
I feel it's the same thing. You are still passing in 2x plus 5 invariably.
Yes, it's just a
You are still
representation.
doing 2
Yeah,
divided by
this
the
is
value.
manipulatable programmatically. Technically, you can still do 2x plus 5 if you are doing symbolic manipulation, but that's, you need another library for that. But with this representation, that's how you would do it. But it's still 2x plus 5, that's the point. You need an equivalent way to rewrite 2x plus 5, but in a way that you can manipulate with code. You get that?
Okay. Yeah, again, I'm just waiting to uncover how we want to implement it.
Because we want to implement it. You're going to write it in Rust. You need to write your polynomial in Rust. Right? So I could be able to give you something like 2x plus 5, and then you can create like a struct in Rust that represents 2x plus 5.
So we can't have 2x plus 5
You just write it as
Rust. Like,
you just write 2x plus 5.
in kind of, you know, it's fine. I don't know.
Like,
No, you can ask it,
you
but it
know,
doesn't matter.
like, if you have a function,
Yeah.
you write a function in Rust, and those represent 2x, like 2
I get what you
times
mean.
the value that you're passing them plus 5.
I get what you mean.
But in JavaScript, you could just say this of this is this. Then when for every time this value is provided.
Yes.
So you're creating a function, like an actual function
Yeah.
of x.
Yes.
Then you now return 2 times the
2 times
variable
that, yes.
plus
Then
5.
for every value that's passed in.
I think it's not fixed. That's why it's not. Because I think what we're trying to do is something that a user can actually
Yeah,
see
but
values.
yeah, that's because we have 2x plus 5.
Yeah.
You can take it any polynomial. I think take it any polynomial.
You want to write it in code
Yeah,
itself.
that's why you're coding the polynomial.
Yeah, I'm putting it for you now. So that I'm coming. There are not more operations you can do on polynomial. So there's the point that I raised where you can collect the polynomial from the user, but technically you could still just write it every single time, which is like fine. But then you now start thinking about things like polynomial multiplication, for example. Like you might want to take a polynomial and take another polynomial, multiply it together to get a new polynomial. That one now you're doing function multiplication, which has no meaning algebraically, right? Like if you're doing 2x times x, it's supposed to be 2x squared. But if you have two functions, and you now say a function and function, you're not going to get another function that someone has return 2x squared inside. So that's why you need like a representation that is like can manipulate. Does that make sense? Okay. So there's multiplication, there's addition, there's what else? You can do division. Okay, let's see. So dents. How do we evaluate dents? Oh wait, sorry. You want to say something?
No, I actually wanted to like
Sparse?
use.
Yeah.
So for the X variable now,
Yes.
like it means that the points we like the number we put into the X
Yeah.
is going to be like number of times we multiply for probably we take a variable. A
Okay.
multiplication variable. Let's say for 2x plus 5 now, let's say 1. For 2x plus 5 now.
I think x is 1.
No.
Okay.
No, like the algorithm.
Okay. So you're setting a variable to 1 first.
Yes, like
Okay.
1. So now, you know that for this one, you have 5,0, right?
Yes.
It means that like it's going to be like 0 times. Is that like normally it's going to be like 0 times that variable, which is so at the end.
No.
It's 0 times.
0 is the power, right?
Yeah, 0 to the power.
So the variable raised to the power of 0, right?
Yeah.
Not times. 5 is the coefficient.
Oh.
Wait, let me write it out so it's not confusing. I'm coming. So this one is the coef, and then this one is the exponent. Okay.
It's not coming.
Oh, it has.
Yes, that's cool.
Okay. But you got the
Yeah.
previous way to do it, right? Where you just like 2 times x to the power of 1 plus 5 times x to the power of 0. Okay. Good? So what of dens?
For this, can I say we look at coefficients
The coefficient?
times
Mhm.
x raised to power the index?
Yes. Does that make sense?
Yeah.
But I need to check. I've seen they're adding, I need to check.
Check already.
For zeros ending.
Yes.
They are-
So you could do it that you could do it one way where you do all the multiplications, right? So you iterate from I equals 0 to length of the array, or you use an iterator. And then you now be like coefficient, that's array index I, times the x raised to the power of I. Yes. So you could do that and just sum it up. Or you could do if I is equal to 0, continue. Right? Because that will not contribute to the sum. So then you don't need to waste that multiplication step. But I won't call it waste. All this is waste. It might look like a waste now, but until you actually measure it before you know whether it's a waste or not. But there are just two different ways to do it. So we also teach you guys how to benchmark. So yeah, when you write a code, you will now write benchmark codes for it so you can know how fast it is. Because when you get to some check and when you get to GKR, you now realize that your GKR is probably so slow. Then we'll now come back and now maybe do some optimizations. Or we'll teach you one way to implement some check, the naive way. Then we'll come back and fix it, but it's going to be terrible. When we did it, we were so surprised. Like, why is this so slow? Why is this so slow? Okay, so we now have to do evaluation now for both pass and dance. So we're good, right? Does anybody not understand how to do it?
In that it's easy to just it's easy to kind of like impute the dance.
What do you mean easy?
You know, it's being that we have a kind of enumerator already.
Okay.
And we could just use that enumerator as our power.
Yeah.
Our power index.
You're talking about rods now, right?
Yes. So it's
So
easy
it's
to
hard to
kind of like
enumerate.
present the dance.
Both of them are easy, yeah. Both of them are easy. You're talking about dance now.
Sorry, I didn't get what we were trying to.
Evaluation for dance.
Okay, for dance.
Yeah. So, similarly now. No. So you, yes. Or like, you use the index of the array as the power.
Okay.
So you just raise x to that power, and then you multiply it by the coefficient which is already in the array. Yeah, so you follow.
But that index is just going to be, it's only when you're using the first method. If you reverse the other,
Yeah,
your index
so
will
that's
actually
length minus 1 minus I. So it just depends on the way you decide to represent it. But it's simple.
So you mentioned GKR. What was that?
So GKR is like the first full snap that I would do. Like every single program can be proven. So ZK is more like there are two uses, right? There's verifiable computation and there's privacy. Right? So the one that the industry is mostly using right now is the verifiable computation. But in the future, we'll now start using like the zero knowledge part of it. See this guy. So so the idea is this. I'm talking about ZK now. I'm giving more philosophical argument. So you have a statement. No, let's talk about the verifiable. So let's talk about ZK first. You want to go to a bar. The bartender is like, you cannot get in here unless you are above 18. Alright? So what's the typical way you prove that? You show them your ID. Now they look at your ID, look at your date of birth, and be like, okay, you're above 18. But now, that person knows more than just the fact that you're above 18. He knows that you're above 18, but he also knows that your exact age, right? So the person has left knowing the exact age when all the person needed to allow you in is just that you're above 18. So what ZK allows you to do, the ZK part of it is that it allows you to prove that you're above 18, but only prove that you're above 18. So if you take the bouncer before the proof and after the proof, and you look at his head, like his brain, like the things that he knows, the only difference between the two guys will just be the fact that he knows you're above 18. He doesn't know any other thing other than the fact that you're above 18. That's the ZK part. That was what I saw. That was like, how is this possible? And then that's when we started like trying to figure out like how this can work. So that's the ZK part of things. Then there's now the verifiable computation part of things, where it's like I do something and you're not there with me. But I tell you that the result of this thing I did is this. So how can I prove to you that I did it correctly, even though you were not there? Do you get? So, and it's so powerful because of the thing that I'm doing can take me 50 years to do. But my proof will be so small, and you will verify it in just 1 second. Do you get? So like the computation becomes asymmetric in the sense that a mobile phone can make sure that a supercomputer is doing right by it. So you have a supercomputer somewhere else that will work for 50 years. I'm not there, I'm not watching this process. And the supercomputer will say, okay, this is the result, and this is the proof. And in 1 second, I'll be able to just verify that proof and know that this supercomputer did the correct thing for 50 years. That's power. That's like why ZK is so powerful right now. And an analogy for why this works is like, you can think of like ZK as having like a small man. So you have like a small man that can sit on your shoulder, right? So whenever I'm giving you something to do for me, let's say you're the supercomputer, I'll give you my problem, and I'll also give you the small man. So the small one is like a lawyer. There's like a confidential agreement that it's not going to tell me the details of what you're going to do, but it's going to be there with you. So now the small one is on your shoulder, is watching you as you're doing every single thing. It's saying that, okay, you did this correctly, you did this correctly, you did this correctly, and then this is the answer. So when you now come back to me, what you do is that you tell me what the answer is, and then you say, take your small man back. Now the small man is technically the proof. So before I accept your answer, I'll ask this guy, did this person follow the steps? And he'll say yes. And I don't need to know anything else other than the fact that this small man said yes. And once it says yes, I accept your answer. So that's technically what happened.
So even if trusting the small one.
The small one is now math.
Okay.
So you don't need to trust.
So that means that even if you guess the answer correctly, but you did not do it.
Yeah. So if you get the answer correctly,
Yeah.
but you not do it, so it depends. It depends.
After you know that.
It depends. It depends.
Someone has failed.
No. So it depends on your circuit. There's something called a circuit. Like there are some things that in ZK now, there are two ways. Let's say you wanted to ask someone to do a multiplication, a division for you. You wanted them to divide 12 by 4. You know the answer is 3. There are two ways to use ZK for that, right? The first way is like, second way you don't even need ZK. That's the point. The first way is that you have a division algorithm. The small man will make sure that you followed each step. So in that case, you cannot just guess because you didn't follow the steps. But then there's another way whereby you say, okay, I don't even need the small man, technically. Just give me the answer. I mean, I will do multiplication on my end. So you said 12 divided by 4 is equal to 3. So me, I'll just say, give me 3, and I'll do 4 times 3, and I'll say that's equal to 12. So there are some computations that one side is very hard to do, while the other side is very easy to do. So division is way harder than multiplication. In that case, it's already asymmetric. Now the point is that you're trying to make the computation asymmetric. You want the prover to do a lot of work, so that the verifier will do very little work. So in that case, the computation is already very asymmetric. In Cairo and others, they call it hints, right? Like you are giving hints to the so the 3 now is a hint. You don't need to prove it. You just give the hint, and I can check it on myself easily. But for things that you can't really check easily, then you now need like that an algorithm that the person must follow, which is like, and the small man will now like tell you that it's just like a more context. That's all this is, just more context. So the more we dive in, the more we start to see like how these things actually work. So right now it's mostly that verifiable computation that we use in the space, right? Like normally also like an Ethereum node, all the nodes have to run the validation. But then technically one node should be able to just run the validation with the small man on them, and then tell everybody that I validated it correctly. And this is the small man. So everybody just asks, did you do it, did you do it, did you do it, did you do it? And then they don't need to waste computation with doing the same thing that everybody is doing. So that's like some of the power of ZK. Makes sense?
Yeah.
Question? Okay. So those are the easy parts. So we're done with, you should be able to represent now. You can choose however you want to represent. You should be able to do the degree. You should be able to do evaluation. The hard one is now Lagrange. And I don't think we should even do it yet. I think you guys should go and suffer and try and do Lagrange by yourself. I feel you need to try and do Lagrange by yourself. Yeah, right. So right now, let's pause now. We'll pause design. So you guys should just try and implement the first 3. Okay? That's representation. Try and implement a representation of a polynomial. Try and represent the degree. Try and implement the degree. So like you represent a polynomial, you ask it for what's the degree. I should tell you the correct degree. And also try and implement the evaluation of the polynomial. Yeah. Now.
You should use sparse or dense.
Depends on you. What is the time? Yeah, in row. When we're saying this, we said prerequisite is what? Is raw and ability to think. So you're supposed to do raw, but now.
X plus 2.
Representation as in convert this to array code.
Let's get
But you guys should just use test, no? You want to test your polynomial this thing, right? So you just create it. How do I put it? Like you should not be collecting 2x plus 5. Instead, you should just put it in your tuple. If you are doing sparse, I don't know if you get what I mean. You get what I mean? So you have your representation of the polynomial, right? If you want to use it, just create it in your test. So let's say you have a test or you have a main function, depending on what you want to use. You just like say let p1 or poly1 equal to, then you create your struct. You get parser. You don't need a parser. Something that will take 2x squared and then try and convert it. No, you don't need all those. You just take the value straight. Yes.
Evaluation function and the
interpolation, and degree.
Okay.
Degree, interpolation, and degree evaluation for now, and interpolation eventually.
Okay, I got it.
Degree and evaluation, yeah. Interpolation when you leave here.
Okay.
Does it make sense?
Yeah.
Don't, they wanted to write pasta.
I thought we start passing over
No.
passing over the course.
No pasta, no pasta.
That's like
Yeah, symbolic this thing. No pasta, that's too difficult for now. Yeah. So I'll try the interface. I'll try the interface. Interface. I think you can use any interface you want, but this is just a guide, kind of. Finite fields. Not yet. Not yet. Just use normal F. Is it U32 or F60? No, it can't be it can't be divided now. There's no division, right? Like,
create a branch for this different skinny environment.
so you will have a crate for each one, but for now, you just do it straight, right? Then later you refactor your code to now have crates. Or if you know how to do crates straight away, just do crates straight away. So you have a polynomial crate, you have a sum check crate, you have a GKR crate. So no finite fields. You can use U32 now, or use size. Yeah. Yeah. So this is the interface for evaluate. It's not necessary. You follow it this way. If you already know how to use finite fields, just go straight. Degree. Sorry. For evaluating itself, right? If you don't know what I'm writing, you don't know what I'm writing. Oh man. So interpolate is giving you a univariate polynomial itself. So I'm assuming that you already have a struct. How do you spell univariate? It doesn't have to be named this. You can name it whatever it is that you want to name it. But interpolate is supposed to sorry. So it depends on how you want to do it. Do you want to? There are multiple ways, right? You could have your x in one. So you can call it x's, right? Which is like this is just a clue. It's not necessary to follow it this way. Vec of u size, and then y is equal to vec of u size, right? This is one way you could do xy, xy, xy. Another way you could do it is you could have a tuple. So that you can call it points instead. And here we'll catch people. So u size, for example. Right? So this one is like, the first one is the x, the next one is the y, xy, xy. So it looks like that one. And then if you know that your interpolation set is always 0, 1, 2, 3, and it's predictable, then you can have another interpolate that does not even require the x's, right? You just have like y's. I don't know if it makes sense. So it depends on how you want to do it. So like if you know that your x's are always going to, your interpolate set is always going to be 0, 1, 2, ascending, then you don't need the x again. It's already implied. But if you know that you're going to be having arbitrary x's, like 2, 3, 5 or something, then that's when you use something like this or something like this. I'll move this one now. So this interface is just to help in case if you are needing a starting point. Then if you have any questions, just ask, alright.
Well, like, does the interface make sense? It does, right?
struct, a univariate polynomial struct. On top of it, yes. So you implement, evaluate, degree, and interpolate and struct.
Is that X5 or X interpolate?
X's.
X?
X's. X. It doesn't matter. It's not, you can name it whatever you want to.
No, I don't want to know that.
X and S. Like multiple
X
X's.
in case I go off.
Yeah. Yes, it depends if you are doing sparse, then vector 2. But if you have vector of 2 poles, then if you are doing dense, it's just going to be a vector of numbers.
Okay.
And last,
Another time.
Sorry. So this
yeah, listen.
this univariate
Is it better? Good?
Sorry, when you use univariate,
Just have to make sure.
sorry.
So I think like we should just for now focus on the degree function.
Yes. Yes. Forget interpolate for now. Just focus on
Forget
degree.
interpolate. Just focus on degree and evaluate. So if you call the degree function, you should count the degree of the polynomial.
Let me hide the interpolate.
You open the rest
Just so that it's not so.
So if you write the first, maybe you create the new
But I don't know how they want to do the new. That's the problem.
Can I do also?
You know, it's more randomish. How you want to collect it. I feel like you should just do the new as like the struct representation. Like just do univariate, open brackets, then fill in the fields. Then there we go. Rather than having a new. You just write your representation directly. Yeah. But for dense, it might be weird. No, dense is always hard.
But it's still just be straightforward.
What about the zeros? Like you want to represent x to the power 7, for example. And then you have to write 6 zeros. And do that for now. Yeah.
First of all, is there a particular polynomial we're supposed to represent?
No.
You can just.
I'm doing a generalized formula.
Oh, we're doing a generalized
Yes.
formula.
So if you want to represent any polynomial,
Oh, wow.
any univariate polynomial.
Okay, secondly, is it compulsory to have the struct?
If you have another way of doing it, then you should be able to do it. So usually you need to hold the coefficients and the exponents somewhere, right? So the proposed way of doing that is using a struct. But you could use any other thing that can hold information. So you could just have like a polynomial as a vec, right? Maybe you don't even need any struct whatsoever. But that would not mean that your degree will need to take in that representation and then check by itself. So it depends on how you want to do it. It's flexible. Theory completeness.
I understand that like everything will not be clear, but that is what I want to do, right?
Yes. So please don't optimize for looking like you have done it. Optimize for actually doing it. Do you get? Like optimize for doing it yourself, like really doing it. So if you are not getting it, call us. Then we'll help how we can help. One day we can just pull you from this road and just say, take, implement, evaluate for this representation.
Let me just ask one random question. Who knows where to start? You have an idea of where to start? Okay, let's hear it.
Like implement the structs, like the univariate poly structs, like the polynomial structs, and then it's going to have like two key object pairs. First one is the degree. The second will be like the vector that stores like tuples of the coefficient and the degree. Sorry, yeah, the power.
Yeah, this pass.
The exponent, yes, and this pass.
And you are saving the degree.
Yes, absolutely.
Okay.
So like, there's like a new function to like create a new polynomial, like a new variable that accepts coefficients, like it's a vector.
Hope everybody is listening.
Please come again.
Okay. So like I'm going to start like implement the univariate poly struct, right? Just create a struct univariate poly, right? That has like two key object pairs and two key value pairs. The first one is the degree, like B32, that saves the degree of the polynomial. And the second one is like the vector, just call it coefficient, I don't know what names to give it. Coefficient that stores like the vector of tuples, right, of like the coefficient and the exponent of each polynomial. Right, so and then I'm going to like implement some functions for that struct. Implement like, implementation of IMPL of the univariate poly and just implement the functions. And then the first function is like just to create a new univariate poly univariate poly struct, right? So
Sorry, when you write some of
I was learning.
You are learning alone.
Kairos.
Okay. Road sorry.
So
Like implementation block.
yeah, the implementation block, like a new function to create a new univariate poly. So you accept the coefficient, that is the vector of how we represented as pass repetition of the polynomial, right? That accepts like a vector of tuples, the coefficient and the exponents, right? So that coefficient is the vector of like the tuples, right? So I'm going to like just look through the tuples. I want to get the degree first. Look through the vector, right? For every tuple, I use the eta to iterate and then map through it and then use a closure. The closure is going to like structure the tuple.
Like not everybody may understand all this, but basically you can just do a for loop, right?
Okay, for loop.
So just say it please.
You can use a for loop to look through the vector, right? And for every value, right, the value is a tuple. So you're going to destructure the tuple, right? To get the first and the second line. So what I'm targeting is the degree. So I'm going to like create a new value. Let's say like just create a temporary value to store like the highest degree that you record. I'm just going to say let's say the temporary value is 0. Right? So I'm going to like as I'm looping through each value, each exponent, right? I'm going to just assign first assign like the first exponent I get from the vector, because now I'm mapping through the vector and the vector values, like each of the value in the vector is a tuple, right? I'm destructuring the tuple, getting the first one which is the coefficient and the second one which is the exponent, right? I'm going to targeting the exponents, and before the loop I've declared a temporary variable above just to like store the degree.
Sorry, is everybody So everybody understand what it is?
So it's using the sparse. That's for the sparse.
Yes, that's for the sparse.
So now, as I'm looking through each exponent, right, I'm going to be assigning like if the exponents I'm looking through currently is greater than like the temporary variable which is 0 at first, it's greater than I'm going to assign it to it. So I'm just going to like find like the highest degree. When I find the degree, right, I'm just going to like instantiate a new univariate construct and just assign the degree that I've got from the coefficient to that degree and assign the coefficients to the coefficient that I'm accepting from the function to the coefficient key there. So I'm creating a new univariate polynomial and I'm returning it at the same time. That's just for the new function to create a new univariate polynomial. Right. So for the degree, I'm just that's it.
But I don't mean to stop there, we still need to include that. But like those are
Yeah, I'm doing
yes.
yes.
You know how to
Then should be, I will just create a vector, instruct that was the vector. Then the vector is going to contain the coefficients.
so everybody here. Very too relaxed.
Okay, I'm going to create a struct. So the struct is going to pull the coefficients in a vector. Then the implementation now is that I'm going to create the implementation function, for instance, the degree. So the degree is going to pass self and return self dot length minus 1. Then the next one will be to evaluate. So if I'm going to evaluate, I will get self, I will get the size, then I'll do my for loop.
Will it be self or length?
Yeah, it has to be minus 1.
Yes.
Self or length starts from 1. If you're saying self, let's say maybe you know the maximum.
That's self dot the room of the struct, the coefficient inside them, the length minus 1. So if I'm having, for instance, now I'm having a coefficient of 5. So I want to be able to know the degree. So since it starts from 0, 1, 2, 3, 4, so I'll do minus 1 to be able to know the actual degree. Then the next one is to evaluate. So evaluate.
But the major thing, like, I felt that maybe most of us did not know where to start. And like, the both of them are giving us like that point to start. Define your struct. Right? When you define your struct, then if you want to go for the sparse representation, you know that your struct is going to hold a vector of tuples. Right? If you want to go for the dense representation, it means that your struct is going to hold a vector of u size, right, based on this. Okay. So, like, after that, then you can now go into like implementing the well, that makes sense. That makes sense, right?
strongly in Rust. I don't know how you guys want to do it. Maybe you guys can figure out a way to coordinate, maybe do some extra classes or something. Just on the basic ideas, right? Like structs, definitions, and the functions, implementation.
Okay, so I was just trying to start everything, but what I want to do now, I just want to do the implementation of the project and just support that for
We'll also end, then you guys will just continue. We might do a walkthrough. We might do a walkthrough where I'll just like implement it on screen. But that's like after everybody has implemented it to an extent.
Here, we're just referencing. You can use it for the click for that calculation. You can repeat it. So then you either becomes a value or zero. So wrapping value that becomes or zero. So if it doesn't return anything, then it becomes zero. If it returns something, whatever it's called, so that goes to
Alright, now guys. Yeah, you can use X. Yeah, X is for yes, but now your formula now, the power thing. I said it's a power formula. Yeah, so what's your X now? Your X is what type? Your X is also X. I think it's power X, power I. Yeah, there's an equivalent
Power
for
I.
power I is items. I think there's another one, but that takes the power as influence. So guys, if you said it's giving you trouble, just use U-text 2. It's giving you trouble.
Yes, you said
So,
So just try structs and then what did you need to know? Like, okay, you have a struct and how you want functions and structs. And like basic functions. I'll do a walkthrough just so that Wisdom. Wisdom. What's representation like? Some cause operation times x of power I nothing looks wrong there.
But the answer looks wrong. You give me like, I'm trying to solve from zero. I'm taking the coefficients.
Yeah. Yeah, this doesn't look wrong at all. Come here.
Even though I don't specify that bracket in before, I need to specify the
I don't think so. But let me check. Maybe that might work. How do you run?
okay, can go on.
C5. C5. Great. 5 on 2 now. 5 was version 0. 2 was version 1. That's 5 plus 2. Yeah, but it is a 2.
It's yeah, it's almost like
Yeah,
it's not like structuring.
that's 5 plus 4. So 0 is 9 if you go to 0. Sublocation was 9 minus 1. Yeah, okay, that was just 0 and 1 now. So sum plus sublocation, which will be 5 times f plus power I 0, which is 1 plus x. That should be 5 f plus then sum plus I and 2 and 2 times still 2 is power 1. So it's false. That was 1 5. Something is wrong. Something is wrong. Oh, I know what's wrong. You like minus 1. So it's not inclusive. Like, when you do 0 dot dot 2, it's just 0 and 1 already. So you need to subtract 1. So it's only doing like constant
Okay, yes.
So I don't evaluate. Now you interpolate. That's a test. Because the monomer is supposed to be general, so it's supposed to be okay, but you won't call it universal for the different because it's not universal. But did you get any error? No. Guys, don't pause, don't stop here actually. You're already testing. So you guys should just go and follow your food now. We'll continue tomorrow. But try and implement it. Then tomorrow I might do a walkthrough of the implementation. So I'll just implement it. Yeah, try and do interpolation. Try and do interpolation. Sir. Well, you guys collect your food and then your mind is better.
You know what? You want to pull out.
Wow, super.
Little by little. There's no.
Just read.
Try interpolate. No? You're looking at it. I'll follow it. For evaluation. So is that raised to the power? Yeah, that's not how it's done.
That's not exhaust.
Okay,
Dot power.
No, that's by
X dot power.
Yeah.
X dot power. Then 2I.
Oh, yeah,
I. Then try this one.
What's my error there?
We need to make sure that the I of us is I32.
Let that try.
Okay, try this one.
You get an error.
Yeah.
That's why I was saying you should convert it to use 32 or
That's
something.
password. I think she's
There is a meta car with the same name.
Oh, okay, we
It's
try
saying
just
I
power.
should
Try
just
just
use
power. Try just power. Not say that.
Okay, so about the
It's supposed to be
I
detailed.
was
So there you do the trying this way, you just convert everything back to this side.
I think
Okay. You done? How far? How's it going?
The interpolate now, we do that like inside. Is that what you call? Ah, can you see the
You can't do it today now, you do it later. We're supposed to do like round.
like with that?
You need to implement like round.
How do we get that? Is it that? Wait, is it that dance now that we used to?
No. You're trying to get the dents. Interpolation is going the other way. Like you don't know 2x plus 5, but you know
Yes.
points on it. So you know the x's and the y's.
And so
Right?
how do you know the point? Okay,
Yeah,
I could
given
just
the
put that
points.
x equals to 0.
You have, yeah, so like 1, 2, 3, 4.
So I give the point.
You give the
myself.
point.
Oh,
Then it's
okay.
now reverse back
So
and
now
give you
reverse
a
back.
dense array in your case
A dense array
that represents 2x plus 5 or something. So you need to figure out how to do that mapping. Yeah. Yeah?
Let's say we collect self.
I know now.
And we collect a set of points that we
So tuples.
set of right? These are we are going to try to evaluate. Inside the interpolate, we are trying to bring out the polynomial. We are trying to evaluate that set.
I bring out the polynomial.
So the polynomial will also have, like, let's say, 2x plus 5.
Yeah. But in your representation,
Okay, in my representation.
whether that's pass or dense.
So,
Alpha.
right.
Oh, yeah, honestly, tuple, okay. Yeah. Yeah, but it looks good. Did you test it?
Yeah, that's
And it's correct, okay?
Yeah.
Yeah. That makes sense. So you're done, except for interpolate.
Yeah, that's good.
So you just try to interpolate by yourself.
Okay, I just, I was doing it outside this.
So you want to now put it back inside. Makes sense. No, I don't want it.
What we are eating? The food you dish for us is we are not
You're done now. We're trying to Why do you complain? Okay, X is written. Yeah, power. That's the power. So that's fine. I want to see the line. One is there. Let me see the line.
Of course, you want to be
There's no 958.
No, 50.
so once you create, because of this,
Oh, this one. Oh, okay.
There is this side.
Yeah, I just
yeah.
said this side.
this one, yes. Exactly. So now I can ignore this one.
Now you can still use this side. Because that was not really the problem. Yeah.
use fast or you use yeah, but it's nice to see why it's nice to see why I have to do so many operations. I bet which function like you use for the inside your spouse.
Using this, right?
So you have to find the master. You have to do them first. Or you have not found the degree. Okay, do the then you now push it into it while you're still then that just becomes another year. What's it's like it's a lot.
I was saying, but you know, my brother said, what is my friend that now 6 I now that turned to 0 1 like that's attached to the first one now becomes 0 1 that's what's that. So now saying that now it's the one that is now used to go. So this is where the function is now. And now so this is 0 1. Now saying 1 times x, the x that we put in this part index that was because you have 0 and I agree with you. See 1 for the first one you see 1 times what's the x that we pass this part and that was happening. So x plus power is power I what I want to say is just say that I so now it does so for the first one. That's not for the second one. And we saw for the first time no we are expecting to just say 0 times no positions 1 times 2 is about 0 plus next one is 2 times 2 again 2 is about 1 next one 3 times 2 is about 0 that's what it is like an outcome that's it
You know that question where you're supposed to get minus 1 and you now got 2,000
when you run
and all of them is are getting 6 square as you say your math is not my
we can see your code back. Let me have an idea. Okay, so
oh sorry I go for 3
you're close. See my line.
Instead of doing
yeah correct
So the degree, then you're using them.
The source that you used for this thing that will help me understand it. You should respect to me.
Which resource?
Any of the resources you use, but more of a self-learning person that should understand it.
So no.
Because from movie I just heard of things like Passa today.
There's no book that has this and spark.
From there I didn't know of this. I didn't even know it's going from.
This self. I don't know. I'm
Take a look at what that's done. So, the brother is small man. I got the values. So far, so good. Thank you.
So interpolate.
Brother, try to interpolate. No.
So,
You have a stroke. I don't know it's a stroke. So I don't need to use a cell. Yeah, you don't need to use a cell. Like,
Yeah, but we get from polynomial. That has like probably like X is in an array and Y is in an array, like 0, 1, 2, so 5. If you're accepting those two guys, that way accepting as a vector, whatever will be a truth, I'm going to just map to it and then try to use that for no use to
Bring him up.
yeah, you have to actually included his interface. You actually have
So for the interpolate, I'm seeing so this is and then are we submitting it? So
this fast.
I was trying to understand this guy.
But your representation, you know, you're
So what I'm saying is now that I want to be sure because what I want to do is this guy. What of these two might be this X? So will do
it will give you 4 and 4. So this one is supposed to be a polynomial that this is supposed to be a polynomial that will find 2. And this was a polynomial that will find 7. So it's the first one. But then these ones are outside are like the second one. Alright, 4 times
Sorry. So normally this is supposed to give me 94.5. This is supposed to give me 90.
Is that a degree? Degree? 9 minus 1 for dense. You want to show me?